Yeah, so there's one exercise left from last week. So it's we had this example or exercise. It's a similar exercise. So it's you have this solid S, solid bounded by well, again the cylinder. So that's the cylinder y squared plus z squared equals to 9. And then you have like 4 planes. Okay, so we have in the planes. So this is from the last week. And the planes, so we said, I think x equal to 0. X equal to 0. And then you have z equals to 0. And then we have y equals to 3x. And then we have y equals to 3. So this is, you know, you have, again, the cylinder, but now we have like 4 different planes. Okay, so again, guys, the number of the equations depends on the problem, depends on the solid, right? Anyway, so I think I tried to sketch this solid S. So let me just remind you quickly what will be the graph of this solid S. So it's it would look like so here's your y-axis, this is x-axis, and then you have this the z-axis. All right, so we have let's say y equals to 3. So this is 3. All right. So I mean, this is the line y equals to 3. Okay. And then we have this plane y equals to 3x. So here we have this. Here, this is y equals to 3x. So of course, when y is equal to 3, then x would be equal to 1. So here, this is supposed to be equal to 1 here. Okay. And then we have the cylinder. So we have, of course, in the back, I mean, in the bottom, we have the plane, the xy plane. That's z equals to 0. And in the back, we have the yz plane, and that's x equal to 0. So, and then we have the cylinder. So we have this. Right. So we have something like this here. Right. So what I was saying, guys, is that so in the bottom here, in this bottom, this is the xy plane. So this is like z equals to 0, and in the back we have the x equal to 0. So in the back of the solid, that will be the yz plane, and that's where x is equal to 0. All right. Well, I mean, the graph is not really good, but anyway. So, and the question was to, I think, if I'm not mistaken, I mean, either the volume or, no, it's not the volume. I think it's, so we have to evaluate the triple integral of the function z, right? Over this solid S. Okay. So we have to find the bounds, right? So as I said, guys, in general, so you have to fix 2 coordinates. So we have this is the 3-dimensional case, right? We have 3 variables. So when you have 3 variables, the best strategy, I would say, is to fix 2 coordinates. For example, let's fix the xy coordinates. Okay, so I'm gonna fix So let's say we fix, for example, and as I said, I mean, you can fix, instead of the X, Y coordinates, you can fix the Y, Z coordinates, or you can fix the X, Z coordinates, right? And see if it works, right? So let's say I'm gonna fix, for example, this, the X and the Y coordinates. Okay, so what does it mean? You fix X and Y coordinates. So it means that you're gonna take the set of the points where the X and the Y coordinates are the same. Okay, so so that means that we have you fix like a vertical line, because you know when you take a vertical line, so let's say you're gonna take this vertical line here. Okay, so this vertical line, of course, is, you know, it's perpendicular to the XY plane, right? In some sense. So here's, it's perpendicular to the XY plane here. You have this right angle. So if you take any point, like this point here, this one here, or you take this one here, all these points, so all the points lying on this line, the yellow line, they have the same X coordinate and the same Y coordinate, okay? So, so all these points, they have the same X coordinate and the same Y coordinate, right? So that's what I mean by fixing the X and Y, okay? So you take this, you know, this vertical line, this yellow line. Now, this yellow line is going to intersect the solid. So the intersection of this solid, of this line with the solid would be, let's say I'm going to pick a different color. Let's say I'm going to pick the brown, okay, here. All right, so it's going to intersect the solid first at the XY plane, right? At the Z equals to 0, right? Here. And then we're gonna have intersection. So with the solid until you arrive at this face here. And this face here is described by, so this is here, this is the XY plane. So this is just a Z equals to 0. Okay. And then your line is going to intersect, your yellow line is going to intersect the solid at the cylinder here. So this is the cylinder, that's the Y square plus Z squared equals to 1, right? So you see this point here, this one here, this point here belongs to the the XY plane, and this point, right? This point belongs to the cylinder, right? This face here, you see this face here, this face is described by the cylinder, right? So so when you fix an X and the X and Y, the intersection with the solid would be the set of points between, you know, the height Z equals to 0 and your cylinder, right? So the intersection with the solid would be between, the intersection with the solid is actually is bounded by, so in the bottom we have the Z equals to 0, the XY plane is bounded by Z equals to 0, and in the top, so in the bottom, that's Z equal to 0, and in the top you intersect the face described by the face, which is the cylinder, and that's Y squared plus Z squared equals to 1. No, it's not 1, I think, sorry. It's 9, sorry. So this is, sorry, this is 9 here. For some reason I said 1. So it's a cylinder, Y squared plus Z squared equals to 9, not 1. So here, this is, and the cylinder y squared plus z squared equals to 9. Okay. No, so this is really important, guys. This is like always, this is like the first step. Whenever you have a triple integral and you want to find the bounds, so decide to fix, let's say, the xy coordinates, or you can also fix another coordinates, right? But the first step is to take this line, whether it's a vertical line or horizontal line or wherever, and then you have to find, you know, the bounds of the intersection. So does it make sense to you why the intersection of my vertical line here, this yellow line with with my solid, would be bounded by, you know, the xy plane and the cylinder? Does it make sense to you guys? Because you see the intersection in the bottom, the intersection is belongs to the xy plane, that's z equals to 0, and in the top of the intersection, you know, the point would belong to the cylinder, because that's this face here, this face here. You see this face here? It's described by the cylinder, right? So yeah. So if you have a trouble with this, guys, please let me know. I mean, I can explain it again, because this is like very important. This is like, that's how we find the bounds in, like, for triple integrals. This is always like the first step. Fix xy coordinate, or fix x and z coordinate, or fix y and z coordinate. Okay, and then you have to find the bounds of the intersection. Okay, Diane. Sure. So what I am saying is, you have your oops, I should use a different color. Okay, so what I'm saying is the following. This is my, this is my solid, all right? So my solid, the faces of the solid here, so in the bottom, you see here in the bottom, that's the xy plane. So this is y, this is x, and this is z. So this is z equals to 0, right? The bottom, the face in the bottom, that's z equals to 0, right? That's the xy plane. And in the top, this one here, this face here, you see this face? This one that's actually belongs to the cylinder. That's the y squared plus z squared equals to 9, right? Now, what I'm saying is, you want to find the bounds, and you decide, for example, to fix the xy coordinate. Okay, so first step is to fix, let's say, x and y. So when you decide to fix an x and y, it means, so in practice, it means that you're gonna fix a vertical line, a line which is perpendicular to the xy plane. So when you fix x and y, it means that you fix a line which is perpendicular to the xy plane. To the xy plane. Okay. As I said, you can decide, instead of x and y, you can decide to fix x and z. So if you decide to fix x and z, you have to take a line which is perpendicular to the xz plane, right? If you decide to fix y and z, so if you decide to fix y and z, then you have to take a line which is perpendicular to the yz plane, all right, etc. Anyway, so here, let's say you decide to fix x and y. So we have to take this line which is perpendicular to xy plane. So we have to take like a random, a random line which is perpendicular to xy plane. So I'm going to take this line here. See this blue line? It's perpendicular, supposed to be perpendicular to my horizontal plane, xy, right? The xy plane. Again, xy plane means the plane which contains the x-axis and the y-axis. So I'm taking this line. Okay, so far so good. All right, so this is this line here. It's perpendicular to the xy plane, right? Now, you are interested in the intersection of this line with your solid. Okay, so this line intersect your solid first in the bottom. it will intersect the solid at, let me pick a different color. Let's pick a green. So first it's going to intersect in the bottom here, your solid. So this point here belongs to the bottom of your solid, right? And the bottom of your solid is actually described by the z equals to 0. That's the xy plane, right? So what I'm saying is the first intersection, this intersection here in the bottom, this point belongs to z equals to 0, to the plane, the xy plane, right? Now, in the top, so you have to imagine you have this perpendicular line, right, going through this, intersecting your solid, right? So in the top, your line is going to intersect the solid at this point, let's say. Okay, but this point will belong to your cylinder, right? This point here, this point belongs to the cylinder. That's the y squared plus z squared equals to 9, right? So what I'm saying is that if I take this random, blue line, this line perpendicular to xy plane, then the intersection of my of this blue line with the solid would be this green segment, right? You have this green segment. That's actually intersection of your solid with your blue line, right? Now, the bottom of the segment, it's a point which belongs to the z equals to 0, and the top of this segment belongs to it's the cylinder. That's the y squared plus z squared equals to 9. All right. So you can imagine here, like, so what I'm saying is if you fix like a perpendicular line to the xy plane, so it's a vertical line. If you take a vertical line, then the intersection of your vertical line with the solid in the top, the point in the bottom would belong to z equals to 0, and the point in the top would belong to the cylinder, y squared plus z squared equals to 9. Okay, so that's what I'm saying here. Now,
and this would only be the first step, Professor. Sorry.
Yeah, this is like the first step. First step, you decide to fix, like, here I'm fixing x and y, but you can also, instead of x and y, you can fix like x and z or wherever and see what happens, right? So here I'm fixing x and y, taking this perpendicular line to the xy plane, right? This blue line, and I check. I have to check, intersection of this perpendicular line to the xy plane with the solid. So I got this, this green segment, right? So now I have to check. So the bottom of this green segment, right? It's a point, of course, but this point in the bottom would belong to the z equals to 0, and the point in the top would belong to the cylinder, y squared plus z squared equals to 9. And this is actually true for any like generic blue perpendicular vertical line, right? If you take this, if you take this vertical line or this one here, of course, I know it's not very clear here, but I mean, if you take any generic random vertical line and you take its intersection with this solid, then the bottom of the intersection would belong to the z equals to 0, and the top of the intersection would belong to the cylinder y squared plus z squared equals to 9. Right? So that means that my height z, so I fix the xy, so I'm looking for the height z, right? So my height z is actually between this z equals to 0 and this cylinder y squared plus z squared equals to 9. Okay, so the height z. So Dylan, does it make sense to you now? I mean,
yes, that makes more sense, Professor.
Okay, perfect. So now
I
can say that my height z varies between. So the height z, it varies between z equals to 0 and z equals to y squared plus, sorry, not y, Z, 9 equals to the cylinder, of course, plus Z squared, right? And of course, here, I mean, my solid is in the above the XY plane, right? So the height Z here is positive, right? So my Z is larger than 0. My Z is positive. Anyway, so my Z is, so what I'm saying is my Z is between 0 and here, well, we have to solve for Z, right? Solve for Z. And of course, if you solve for Z, you're gonna get, because of the even power, you're gonna get plus or minus, right? 9 minus Y squared. But because my Z is positive, right? Here, my Z is larger than 0. It's above the XY plane, right? My Z is positive. So Z is positive. So then my Z would be between 0 and plus square root of 9 minus Y squared. So I'm fixing X and Y, and I'm saying the high Z varies between these two equations, right? Once the X, Y, and Y are fixed. Okay, so this is like the first step. You fix 2 coordinates, and you try to find the bounds for the third coordinate, right? So that's like the first step. That's always the first step. Okay, so just remark. So this is always the first step. So fixing 2 coordinates and finding the bounds of the third coordinate. All right, so okay, so I got the bounds for Z. Now I can, now is step 2. So this is, we said this is step 1. So now step 2 would be to find, of course, the bounds for X and Y. Okay, so that's for Z. Now step 2. So I'm gonna find the bounds of the other 2 coordinates. So in this case, it's the X and Y, right? So in our case, in our example, that's the X and Y coordinates, right? So now, how do we find the bounds for the X and Y coordinates? Well, I tried to explain this in last week. So I said, sorry. So we have to find the projection of your solid into the XY coordinates. Okay, so we have to find the projection of the solid. So in this example, the remaining 2 coordinates are X and Y, right? So we have to find the projection of the solid into the XY plane. Right? That's where Z is 0, of course. Okay. So what will be the projection of our solid into the XY plane? Well, let me sketch very quickly the solid again. So here in the bottom, I said we have this is, this is Y equals to 3. And here we have this is, so this is Y-axis, X-axis, Z-axis. And here in the bottom, this line here, the equation of this line is Y equals to 3x. Okay, and then of course, in the top, we'd have the right? In the top, we'd have the cylinder. But anyway, so I'm interested in the projection of the solid into the XY plane. So as I said, I explained last time. So the geometrically, so what we do to find the projection of the solid into the XY plane. So we are supposed to take the points in the solid, right? Like let's say this point here in the solid, and I'm supposed to take the line passing through this point and orthogonal to the or perpendicular to the XY plane, right? So like here in this case, I'm going to have this line. So the intersection of this line, orthogonal to perpendicular to the XY plane, with the intersection with the XY plane would be this point, right? Now, if you do the same for all the points in the solid, then you're going to get, so then the projection into the XY plane would be this face here. Right? So this face is described by, so if you take just the X and Y coordinates, so the bottom, so if this is your X, this is Y. So we have the line Y equals to 3. This is, you see, this is the line Y equals to 3, right? So here's my line Y equals to 3. And let's say this is 3 here. Right? So this is Y equals to 3. And then the other line, or the other side, this one here, let's pick blue. So this line here, this is the line Y equals to 3x, right? So here is Y equals to 3x. So this is Y equals to 3x, right? And here, of course, this should be 1 here, right? Because when x is 1, Y would be equal to 3, right? So this is the point 1, 1, 3. Okay, so the projection of the solid into XY plane would be this this region here, this triangle, right? And that's exactly the face in the bottom here. Okay. Now all I have to do is to describe this, this triangle using the XY coordinate. I mean, you can start with the X, or you can start with Y. So for example, you can say, your Y, for example, is between, you have this triangle. We have this triangle here. Okay. So it connects this line here in the top, or this side here in the top, to this point. So here in the top, I have Y equals to 3. And this point here in the bottom, that's Y equals to 0. The Y coordinate is actually Y equals to 0. Okay, so you can say, well, then my Y is between 0 and 3. Okay, now my X, so my X is between these two functions here, this one here and this one here. So this is, let's say this is G of X, and this is, let's say, H of X. Okay. So here, this line here, this is just the y-axis, so that's x equal to 0. Sorry, it's g of y. Now we need the functions of y. Sorry, y is between 0 and 3, so here should be functions of y. Sorry, so this is g of y and h of y. Okay. So anyway, so this is this line here. This is just the y-axis, so it's x equal to 0. And this one here, this is y equals to 3x, right? And if you solve for x, so then that will be x equal to y over 3. So this h of y is y over 3, right? It's supposed to be a function of y here, because y is fixed. It's between 0 and 3. Then we are looking for functions of y. Right. So all I'm saying, guys, here is that I have y equals to 3x, so I'm solving for x, so that's y over 3. So this is, here's my function of y, h of y. Okay. So my x is between 0 and, so this is, here's 0, and here's y over 3. Okay. So anyway, yeah, so I got the bounds for y, I got the bounds for x. Now we can integrate. So now we can, so the conclusion here, so z is between these two functions of x and y. So z is between 0 and square root of 9 minus y squared. And then my x and y, so x we said it's between 0 and y over 3, and y is between 0 and 3. Is there any question, guys, about these bounds? So first, you see how it works. So first I fixed x and y. I got the bounds for z. And then you take this projection into the xy plane. That will be the bottom, the face in the bottom, right? And that will be just the triangle. And so you get the triangle, of course, it's an elementary region, right? I mean, we remember our discussion about elementary regions in the plane. So we got this elementary region. It's just a triangle, and then you can just describe your triangle by saying y is between 0 and 3 and x between 0 and y over 3, right? Or of course you can, instead of y between 0 and 3 and x between 0 and y over 3, you can say like x is between 0 and 1, right? And y would be between 0 and 3x. Okay, it's up to you. I mean, of course. Any question about these bounds, guys? All right, perfect then. So that's the bound. So I think the most difficult part here with the integration is, especially the triple integrals, is to find these bounds. So now we can evaluate. Our triple integral function z, the volume element over this solid S. So, well, my y is between two constants. So the last integral would be with respect to y. Okay. Here, let's say my z, I started by the bounds for z. So here z, let's say, is between two functions of y and x, because I project my solid into the xy plane, right? So this is supposed to be functions of x and y. This is h of x and y. All right, and then here I got my x between two functions of y. Let's say alpha y and beta y. Okay, and then y is between two constants. So then I have to integrate, let's say, first with respect to z, right? So I have z. Well, here's my function z, of course, first. Now the volume element, so I integrate first with respect to z, and then with respect to x, right? Because x is supposed to be between functions of y. And then the last integral would be with respect to y, because y is between two constants, right? So it's dx here, and then dy. So z is between the 0 and square root of 9 minus y squared. X is between 0 and y over 3. And then y is between 0 and 3. Okay. So yeah, so here you integrate z with respect to z. Right? So that will be z squared over 2. So I'm going to keep the integral with respect to x and y. So this is 0 y over 3. So here is going to be z squared over 2, evaluated between 0 and this square root of 9 minus y squared. Here we have a kind of good news because we have a square, z squared. So then with the square root of 9 minus y squared, that would cancel out. So here's dx and here's dy. So if you replace z by square root of 9 minus y squared, then that will be equal to, because of the square, so the square is going to cancel out with the square. So that's 9 minus y squared over 2. And of course, if z is 0, everything is going to be 0. So that's just 9 minus y squared over 2. Now we have to integrate with respect to x, right? Here, with respect to x. So this whole thing here is just constant. Okay. So the integral would be the constant times x. Oops. So here's the 0 peak, the constant, which is 9 minus y squared over 2 times x. Okay, and this is evaluated between 0 and y over 3, and then dy. All right, so now x is equal to y over 3, so that will be this is 0 3, 9 minus y squared over 2 times this y over 3. X is 0, then it's going to be 0. Everything's going to be 0. So it's just this 9 minus y squared over 2 times y over 3. And then I guess you guys know you can just, this is not really hard to integrate with respect to y. So, I mean, if you multiply, that will be 9y over 6 minus y cubed over 6 again, right? dy. So you integrate, so this is 9y y squared over 2 times 6, that will be 12, and y fourth, 4 times 6, 24, and between 0 and 3, all right? Anyway, so I guess, well, I mean, you can continue here, the computations, guys. Just replace y by 3. Right? And you're going to get your answer. I think, let me see if I have the answer. It's somewhere in my notes. Well, I mean, I can, well, no, yeah, here's the answer. Actually, the answer is going to be 27 over 8, all right? I don't want to do the computations here, guys. It's just too many fractions. I mean, it's fractions here. So then the answer is just 27 over 8. But anyway. Any question, guys? Okay, no questions. Then, so this is, again, this is similar to the problem 4 and 5 in the homework. Yeah, so I think we are done actually with the triple integrals. So then I guess we can move to the next section, which is the change of variables. This is actually a very interesting section because we'll see, I mean, sometimes, some integrals are very difficult to, very hard to evaluate, but with some just a change of variables, your integral becomes very easy actually to compute. Anyway, is there any question about this triple integrals, about the homework? Otherwise, I'm gonna move to this new section. I guess there's no questions. Okay, good. All right, so let's move to the next section then. So next section, yes.
Sorry.
Yeah, sure.
Homework number 2 due?
Thursday.
Oh, okay.
So yeah, so I mean, during this semester, I mean, what we're gonna do, I'm gonna post the homeworks on, let's say, Wednesday or Thursday, and then they are due like Thursday next week. okay, all the time. Okay, yeah, so is there any other question, guys? Nope. All right, so let's move to the next. What's going on here? All right. Okay, yeah, so change of variables. This is a very nice section, actually. It's not really bad. Let's see how the change of variables would affect the integral, right? So we're gonna start with studying a little bit the transformations, let's say in the plane first. So, and actually we're going to be interested in how transformations change regions in the plane, right? So the goal here, so we are interested in how transformations let's say change regions or solids. So regions in the plane and solids in the space, in the either the plane or the space. Okay. So what do I mean by transformations? So instead of definition, I'm going to go first with examples. Okay, so we can see you can see how these transformations work. Some examples, and then I will probably define, like in very general way, what I mean by transformations. Anyway, so let's start with some very basic, simple examples. Example one. Okay. Well, so I have this function or map t. So let's say that t. So we're gonna start with the plane, right? So we're in the plane. So when I say in the plane, so it means, of course, we have only two coordinates, two axes, the xy, the x and the y axis, and so the plane that will be R2. Okay, and when I say a space, that will be R3. Okay, R2, it's because it's R cross R. That's because my x belongs to the number line R, and y is in the number line R, right? So that's why it's called, the plane is called R squared. It's just because it's R cross R, where x is in R and y also in R. R, of course, is just the set of real numbers, right? Anyway, so I have this function or map t from R2 to R2. Okay, so it's from R2 to R2. So again, R2 means the plane, right? This is just a plane, right? So and let's say in this example, my t of so I'm going to use instead of the variable x and y, I'm going to use u and v. So let's say t of u and v is equal to u plus 1 and v plus 2, right? Well, anyway, so you can guess here, guys, this t, I'm using the letter t because t stands for actually transformation, right? So when I say transformation, I mean a function or a map, let's say between a map or a function between R2 and R2, which is, let's say, differentiable. So t, a transformation, that means that t is a map or a function of the plane, which is continuous and differentiable. I need the derivative to exist, right? So differential. Anyway, as I said, so we have this t of u and v equals to u plus 1 and v plus 2, right? So as I said, we are interested in how t changes regions in the plane. So for example, let's say my region is a square. Let's say, so I have this, so let's say R, so this is my region in the plane, is equal to the square. It's a square. It's the square here. It's just let's say 0, 1 cross 0, 1. Okay. Now, so here this is t of u and v. So let's say this u plus 1 is equal to x. So x is equal to u plus 1, and here this v plus 2 is equal to y. Okay, so we have y equals to v plus 2. Right? Anyway, so let's take this square and see how this transformation t change our square, right? So we have here our region. It's a square. So let's say here you have u axis and v axis, and you have this square 0, 1 cross 0, 1. So let's say this is 1 here. This is 1 here. So we have this square. So this r. Okay, that's my region. That's a square, right? Now, so the vertices of the square. So we have this is the origin, of course. This is 0, 0, 0, 0. Here, this is 1, 0. This is this vertex here. It's 1, 1, and this vertex here would be 0, 1. Right? So let's see. Let's see what happens to the vertices under the transformation t. Right? So let's see what happens to the vertices. So, for example, what would be t of 0, 0? Well, t of 0, 0 is just u is 0, v is 0, so then that's 1, 2, right? I'm just replacing here, guys, u and v by 0, 0, right? If you take another vertex, let's say vertex 1, 1, then t of 1, 1 would be, for example, 2, 3, right? Etc. Like t of 1, 0, that will be equal to 2, 2, right? And then the last vertex, so 0, 0, 1, 1, 1, 0, and then 0, 1, right? So that would be 1, 3. Right. So the image of the square under this transformation t would be actually, so here I'm going to use, so here I'm using u and v coordinates. Now I'm going to use x and y coordinates. So here's the x coordinate, so x axis, and as I said, x is supposed to be equal to u plus 1. And here, this is the y coordinate, so and y coordinate, so the y is equal to v plus 2, right? That's my v plus 2. Anyway, so like the image of the vertex 0, 0 is 1, 2, right? So the 0, 0 is actually shifted to 1, 2. So I'm gonna need probably 1 here, 2, and then I'm gonna need, I guess, 1, 2, and 3. 1, 2, and 3. All right. So t of 0, 0, we said it's 1, 2. So we're gonna get this vertex here. This is 1, 2. That's so what I'm saying 0, 0 is actually shifted to 1, 2, right, etc. And then you're going to have t of 1, 1 is 2, 3. So we're going to have 2, 3 here. 2, 3. We're going to have 2, 2. And we're going to have 1, 3. Right? But anyway, so the idea here, guys, is that the square, so this red square here, this red square, right, 0, 1 cross 0, 1 is actually shifted to the this new square, this green one here, right? So, and this square here, it's actually, this is the square. So let's call this square here the square D, and that's actually, so it's this interval 1, 2, right, cross the interval 2, 3, right? So this is 1, 2 cross 2, 3. Okay. So anyway, so what we are saying here, guys, is that the image of this square 0, 1 cross 0, 1, the red one, is actually, it's also square, and it's the square 1, 2, 2, 3, right? So the image of the square R, which is 0, 1 cross 0, 1, is the square. It's also a square, is actually the square D, which is 1, 2 cross 2, 3. Okay. So in other words, this, you started with this red square 0, 1 cross 0, 1. So this 0, 1 cross 0, 1 is actually translated to this square 1, 2 cross 2, 3, right? So conclusion. So here, of course, this is, so here's my transformation T, right? So conclusion is that, so T so under the transformation T, okay, R is, the square R is actually translated to the square D. So all we did here, guys, is just remove the square 0, 1 cross 0, 1 to the square 1, 2, 2, 3, right? Anyway, so this is just the first example of a transformation. So a transformation is just this map in the plane, and again, we're interested in how this transformations are going to change regions in the plane. So I just picked here a square, but of course your region R could be like a rectangle or a triangle, and you can see what happens to your triangle or rectangle or wherever, right, under the transformation T. But anyway, let me pick a different transformation, okay? So this is just actually a translation. So I'm gonna pick another example. So this is T of U and V is equal to 2 times U and 3 times V, all right? And so if you do the same thing, so if you start with this square, let's say R is the square 0, 1 cross 0, 1, then if you study the image of the square, so then so here's my u and v. So one, this is one, right? And so this is x is equal to 2 times u. All right, so this is my x is equal to 2 times u, and my y is equal to this 3 times v. All right, y, this is a y axis, so it's equal to 3 times v. All right. Anyway, so the origin 0, t of 0, 0, of course, is just 0, 0. So the origin is fixed. T of 0, 0 is just 0, 0. So the origin is fixed. Let me just write it down here. So t of 0, 0 is 0, 0. So the origin is fixed. Right. So again, this is my origin r, the square. So the image of the origin is 0, 0. But I'm gonna need here 1, 2. This is 1, 2, 3. But then the image of the vertex, let's say 1, 0. That would be 2, 0, right? So you stretch the vertex 1, 0 to 2, 0, right? So this is here. You're gonna get the image of the vertex 1, 0 would be 2, 0. The image of the vertex 0, 1, you're gonna stretch it, right? You're gonna have the vertex now 0, 3, right? And the image of 1, 1, that's 2, 3. So you're gonna get this. So now the image of my square R, it's not a square anymore, right? It's a parallelogram. It's actually a rectangle, right? So this is my rectangle, D. So D. So here now D is a rectangle. Okay. So what I'm saying, guys, so this transformation here in this case, it would fix the origin, but it's going to stretch all the other points, all the other vertices, right? And so the image of the square in this case would be a rectangle. It's not square, right? So the image so in this case, the image of square is, it's not a square anymore, it's actually a rectangle. Now, right, you stretch your square and you got this rectangle. Now, if you can compose the first and this the first example with this this example. So if you take the composition of these two transformations, that will be my third example. So let's say in this third example, my t of uv is equal to, I'm gonna stretch by 2. So I'm gonna multiply u by 2, and then I'm gonna shift by 1, so plus 1. Do the same for v, stretch by 3, and then I'm gonna shift by 2. Right. So this is kind of, this is you start with 2 u times 2, right, and then now u times 2, v times 3. That's my transformation, in the second example, my transformation in the second example to u times 2 and then v times 3, right? And then I shift using, so here's plus 1, here's plus 2, and that's exactly my transformation in the first example, right? In the first example, I had u plus 1, I had this plus 1 here and this plus 2 here. So what I'm saying is that this third example is actually a composition of the first two examples, right? This is, so this t here is a composition of the first example and the second example, right? So you have to stretch and then you have to shift, or you have to translate, right? Right. Anyway, guys, let's do a last example. So this example less obvious than these three examples. So in example number 4, so I mean, my remark here is that in this three examples, each component involve only one variable, right? Like here in the first example, the first component is u plus 1, so it involves the variable u, not v, right? Only one variable. The second example, same thing. It's v plus 2. It only involves v, right? So there's only one variable in each component, right? Same here in the same here in the example number 2. In each component, we have only one variable. And same here for number 3. Now, in the example number 4, I'm gonna have, so in 4, example number 4, and last example, and then I will give you like a very general statement about these transformations. So in example number 4, I'm gonna have t of u and v is equal to u plus v, and then u minus v. Right. So this is less obvious example because each component involves both variables, right? In each component you have both u and v, right? So this is less obvious because each component involves both variables. Okay, so my question here is how does, okay, here's an exercise, very easy exercise, I guess. So my question for you guys, so exercise, how does the square 0, 1 cross 0, 1 transform? Okay, and again, just be careful because this is, no, I mean, this is less obvious that because each component involves both variable, not just one. All right, so I'm going to give you a couple of minutes, guys, to think about this transformation and what it does to this square, this square 0, 1 cross 0, 1. So all you have to do, guys, try to find the image. So what I'm saying here, so the question is to find the image of the square under this transformation t, right? That's the question is, so find, what will be the image, find the image of t, sorry, the image of the square, 0, 1 cross 0, 1, under the transformation t. Okay, I'm gonna give you a couple of minutes to think about this. So our goal today, I'm not sure if we're gonna finish. I don't think we're gonna finish this today, but anyway, so our goal would be to, guys. I mean, integrals like double integrals or triple integrals. It's about, so if you integrate like a function one, the constant function one, then that will be let's say the area of your region or the volume of your solid, etc. Right? So why we are trying to study these transformations is because we want to see what happens to the the area of, like the area of a rectangle or the area of a parallelogram under a transformation T. Because in some sense the change in the area or the change in the volume, that will be that would correspond to a change in your integral, right? Because the main idea about integrals is to compute like the areas or the volumes, right? Um, so so we are doing these transformations because we want to see what happens actually to the area of our regions or the area or the volume of our solids under some transformation T. So for example, we said, like in the first example, we have the image of a square is just is also a square, and actually the two squares, they have the same area, right? But then in the second example, the image of a square was like a rectangle, and the image of the area of our rectangle is actually larger than the original square, right? But so we're gonna see how the area of the two regions relate. Okay, what will be the relation between the area of the two regions? Okay, guys, any idea what will be the image of this the square 0, 1 cross 0, 1 under this transformation T? Would be the image would be a square again, or a rectangle, or a parallelogram?
I think I got a parallelogram.
Um,
I'm not sure.
okay, now actually it's gonna be a square. Um, well, probably I didn't explain really well how to how we find the image of our square or our square, right? So okay, so probably I should solve this. So what I'm saying, guys, here is that right, we start with the square, right? So this is my square. This is U. This is V. This is 1. This is 1. This is 0. Okay, so we have, this is my square R. Okay, so R is 0, 1 cross 0, 1. So what I'm gonna do here, guys, because as I said, this example, this transformation is less obvious than the previous one because each component involves both variables. So it means this is this transformation. It's not like it's not like a horizontal or vertical shift. It's not like stretching your square, right? Because we have both variables involved in this example. But anyway, so what I'm gonna do, I'm gonna try to see what will be the image of the sides or the edges. So for example, let's say we start with the bottom edge, so the bottom edge here. So the bottom edge is this side here, this one here. This is the bottom edge. All right. So what's the image of this bottom edge under the transformation T? Well, I mean, what will be the equation of this bottom edge, right? That's just, I mean, the V coordinate is, that's the U axis, right? So the V is equal to 0, okay? So if you want to describe this bottom edge, you can say this bottom edge is given by U0, right? If you have a point here in this bottom edge, that will be U0. So the coordinates are actually just U0, right? The V coordinate is 0. So then, I mean, so the bottom edge is just described, can be described by U0. Now, what's the image of U0? Well, the image of U0 under my transformation T is just, well, supposed to be, I mean, T of UV is equal to U plus V and U minus V, all right? So then T of U0, V is equal to 0, would be equal to U, right? And of course, here U is between 0 and 1, right? With U between 0 and 1, right? In this bottom edge, the U coordinate is between 0 and 1. So what I'm saying is the image of this side or this edge would be the edge UU with U between 0 and 1. Now, let's say if you want to take the top edge, well, the top edge would be this side here, right? This side here. This side, I mean, the V coordinate, of course, is equal to 1, right? So here, the V coordinate is equal to 1, and the U coordinate is just a number between 0 and 1. So this is here, this is U1 with U between 0 and 1, right? So the top edge, sorry, can be described with as the set of points U1, right, with U between 0 and 1. So then T of, what will be T of U1? What will be T of the image of the top edge? T of U1, that will be, I mean, V is 1, so that will be U plus 1, U minus 1, with U between 0 and 1, right? You can do the same for the left and the right edges. So this is so let's say left side or left edge. Okay, so that will be this side here, this one here, and this is of course this is where U is equal to 0. This is 0 V between 0 and 1. So this is 0 V between 0 and 1, and so T of 0 V would be equal to actually V minus V, right? Just replace U by 0. Right edge, I'm going to use the blue here for the right edge. That's where U is equal to 1. So this is the right edge would be the set of points 1 V with V between 0 and 1. So for the right edge, so that's a set of points 1 V. Of course, V here between 0 and 1. V between 0 and 1. Here it's V between 0 and 1, of course. And T of 1V is just V plus 1 v plus 1 and 1 minus v. Okay, now we can try to graph these edges, the image of the edges. So for example, so here's again my u and v. All right, and here's my, so this is 0, 1, 0, 1. So I have this square, right? The bottom edge, let's call the bottom edge, this is the bottom here. This is the top. This is the left here, left edge, and this is the right edge. Okay, so for example, we said the bottom edge, the image of the bottom edge, u0, that would be uu, right? We said t of the bottom, u0, it's uu, right? So uu, it means that the x coordinate is equal to the y coordinate, right? This is supposed to be x. So x is u plus v here, and here's y. This is u minus v. Okay. So uu, it means that this is supposed to be my x, and this is supposed to be my y, right? So x is equal to u, y is equal to u. So then x is equal to y, right? X is equal to y. So both of them are equal to u, right? So the x and y coordinate both are equal to u. So that will be this line here, the diagonal, right? So the image of the bottom edge would be the diagonal here, and u, of course, is between 0 and 1. So x and y, with x and y here, so x is equal to y is equal to u. They are between 0 and 1, right? In the bottom, u is between 0 and 1. So here we're gonna go, so this is 1 here, this is 1. Okay, so that's the image of the bottom edge would be this diagonal, y is equal to x, with y and x between 0 and 1, right? This is, let's say, so this is y is equal to x. Okay, so this is the image of the bottom edge. All right, does it make sense to you guys? You see how I found the image of this bottom edge? I mean, it's just some standard computation, but anyway, it's not that important actually. But I'm just trying to show you how we can find like the image of these squares and their transformations. But anyway, so what else? Yeah, so for example, if you take the left edge, right? The left edge, we said its left edge is 0v, right? The image of 0v is v minus v, right? So this is supposed to be x, this is supposed to be y. So your x is equal to minus y, or y is equal to minus x, right? X is v, y is minus v, so then y is equal to minus x. Okay, and of course x between x and v is between 0 and 1, right? So with x, which is v, between 0 and 1. So y minus x is going to be also diagonal, but it's going to go down. So the image of the left edge would be, I'm going to need -1 here, because x, so y is equal to minus x, right? X is between 0 and 1. So my x is between 0 and 1, So that will be this line here, y equals to minus x, right? This is y equals to minus x. All right. So that would be the image of the left edge, right? This is the image of the left edge. Right. Anyway, so I hope you see how it works, guys, right? I'm trying to find the image of the edges. I have the image of the bottom edge, left edge. Now for the right edge, you're gonna have this. So this is 1, 2 here. You're gonna have this side here, this one here. All right. This would be the image of actually the right edge. All right. And finally, the top edge, the image of the top edge would be this line or this side here. This is the image of the top edge. Okay. So actually, so the image of your square is going to be this square here. So this is, of course, I'm going to use probably a brown here. All right. So here's the image. This would be this square here. Okay.
Professor, that's what I got, but I did it like a completely different way.
Oh yeah, I mean I mean there are a lot of different ways actually to find the image of the square.
I just want to know.
Yes.
I did it like how we were doing all the other examples where you had the
there's the vertices.
Yeah.
The vertices. Yeah, but
Yes.
the thing, yeah, you know what, because in the previous examples, we had each component involves only one variable, right? So it means that your transformation would shift, or you would stretch your square, right? In some sense, right? So it's kind of, yeah, that's why actually I just took the images of the vertices, because your transformation was either stretching or shifting your square, right? In some sense. So that's why I took the images of the vertices, right? But here it's not obvious actually exactly what would happen to the square, because each component involves both variables, so it's neither a shift or a stretching, right? So that's why I try to find the images of the edges to see exactly what will be the image, because this is less obvious than the previous examples. You see the difference?
Yeah, but is it wrong how I did it?
No, it's correct. It's correct.
Okay.
I'm just saying that just to make sure 100% that my answer is correct. That's why I try to find the images of the edges here in this case, because both components, they involve the both variables. So it's not a stretching, it's not a shift. So so you have to be careful. All I'm saying here, you need to be a little bit careful, because it's neither a stretching nor a translation or shifting, right? So yeah. All right. Okay, so we got the square. So what we are really interested in, guys, as I said, is the relation between, what will be the relation between the areas of the two regions, right? So here, the area of my original initial region R, which is a square. Of course, a square. The area of the square would be just so the area of my square R, which is 0, 1 cross 0, 1, is just, of course, it's just the base times the height. It's equal to 1 times 1. It's equal to 1, right? Now, my question for you guys: what's the area of this region? This region D here, this square D here, area of D. The image of R, or Okay, well, as I said, it's just so we have to, it's just a square, so we have to just compute the length of the edges here. I mean, this is just a simple exercise, very simple exercise to find the length of the sides here. I mean, like this side here, I mean, it goes from, you can just apply the Pythagorean theorem, right? I mean, this is 0, 0, this is, here's 1, 1. You have this right triangle, right? The sides here, this side is 1, this is 1, here's 1. So the hypotenuse, the yellow, the yellow side, the hypotenuse of my right triangle would be square root of 2, right? So this is square root of 2. We can do the same here for this side. Right triangle side would be just square root of 2. The length of the side would be square root of 2, right? Anyway, so all I'm saying, guys, is that if you want to compute the area of the image, that will be actually square root of 2 times square root of 2, which is 2. All right. So you see here, there's a change in the area of our our square, right? It went from 1 to 2, right? So well, so in the next theorem, I will explain what would be the relation between the area of the two regions. So let me just say here, guys, all these examples are called linear transformations. So you see here, guys, all we did to the variables u and v, like here. So all we did is we multiplied, let's say, u by 1 here, plus 1 times v, and here we multiplied u by 1 plus v times -1, right? We just, we have the sum of some constant times u plus another constant times v, right? And the same here with the previous examples. Like here, all we did is we multiplied u by some constant, right? And here also, here v by some constant, right? So anyway, so all I'm saying is that in general, so if you have a transformation of the form, so this is a general statement. So in general, so if you have a transformation t of u and v equals to a u plus b times v, and then c times u plus d times v. The a, b, c, d are constant. Okay, this is really important, right? They are constant. All right, so you multiply u by constant, and then you add some constant times v, right? So if you have such a transformation, actually such transformation is called such transformation t is called a linear transformation. Okay. Again, you're multiplying u by some constant plus another constant times v, right? So that's what we call linear transformations. And actually, I don't know if you did some linear algebra. I mean, you can write this transformation as a matrix times the vector uv. I mean, if you, I don't know if you did some linear algebra, but you can write this transformation t of uv as the matrix a, b, c, d times the column u, v. Right. I mean, here we have like, this is supposed to be like multiplication of matrices. How do we do multiplication of matrices? I mean, you don't need to know for this course how we multiply matrices. I mean, it's not a linear algebra course, but let me just here for your information. So like here in this case, we have this square matrix times this column, the UV. So what we do when you multiply, you take the first row here, first row times the first column here. So A. So it goes like, it goes like A times U plus B times V, right? That will be first component. And then you take the second row, the CD, you multiply C by U plus D by V, all right? Anyway, so all I'm saying is that it's called linear transformation. It's because, you can write it as some matrix times UV. Okay, so it's called linear transformation of the plane. Of course, we have UV. That's just the coordinate. So we have linear transformation of R2. R2, of course. Okay. So for example, back to the example number 4. In the example number 4, we had like T of UV is equal to U plus V, right? And then U minus V. So in this case, like A would be equal to 1. We have 1 times U. So that's like my A plus B times V. So here's 1 times V. So this one would be like my B. And then C times U. So it's 1 times U. So this is my C minus, of course, this is a -1. So -1 would be my D, right? So yeah, so what I'm saying is that this is a linear transformation because, you can write this T of UV as a matrix AB. So AB would be 1, 1, and then CD, that would be 1, -1, right? AB here in the top in the first row, and the second row we have CD, right? So it's 1, 1 in the top first row, second row it's 1, -1 times UV, right? Okay, so I hope it makes sense to you guys. So that's what I call linear transformation, like constant times U plus another constant times V in both components. Anyway, so there is a very, very special, so these linear transformations, they have very special properties. So proposition or theorem, and in the last 3 minutes, and I will come back to this next time with more examples, of course, but let me just write down here for you the theorem about these linear transformations. So if you have a linear transformation T, so let T of UV is equal to some matrix A times or let me write down first A, matrix A. So so let's say let the capital A is the matrix A, B, C, D. Okay. Okay. With determinant of A non-zero. So what's the determinant of A? So determinant of A is just C here, of course. So determinant of A is equal to A times D minus B times C. Okay, that's what I mean by determinant of A, matrix A. All right, you are supposed to like it's like a cross multiplying here, right? AD minus BC. Okay, that's what I call determinant of A. Anyway, so you have this matrix A with determinant non-zero, And let's say you have define the transformation T. Let's say you have this transformation T, which is linear transformation given by this matrix A. So A is T of UV is equal to A times UV, right? Like here in this example number 4, right? Anyway, so if you have this transformation T defined by this matrix A, then actually T takes parallelograms to parallelograms, right? And vertices of parallelograms to vertices of parallelograms. So this is not always true, guys. It depends on the transformation T. We'll see later next time more examples where this is not true. So for example, you would have, I would see some transformations which takes like a parallelogram or a rectangle to I don't know, to a circle or to a disc, okay, etc., etc. So that's not always true, okay, for transformations. But what we are saying is for this special kind of transformations, linear transformations, the image of a parallelogram would be a parallelogram. And if you have a vertex of a parallelogram, it's going to take a vertex of a parallelogram to a vertex of a parallelogram. So to vertices of parallelograms. And one more very interesting fact is that moreover here, so the area of the image, the area of a parallelogram, the area of let me state this in a different way. So moreover, if let's say if D, let's say R is a parallelogram. I'll just finish with this theorem, guys, and we'll come back to this next time. Sorry. So R is a parallelogram, then the area of the image of R so the area of the image of R is equal to the absolute value of the determinant of the matrix A times the area of R. Okay. So the relation between the two areas, the area of the original or the initial parallelogram and the area of the image. So the relation or the ratio is given by this absolute value of the determinant of A, determinant of the matrix A. Anyway, guys, I'm sorry. Again, I'm over time. So I will come back to this next time on Thursday, and I will give you examples, more examples, right? So again, guys, homework number 2 is due this Thursday. And if you have a question, please email me anytime. All right. We'll see you on Thursday then. Thank you, guys. Thank you, everyone.
Bye, Professor.
Bye. See you next time. Take care and stay warm, of course. Thank you, everyone.